Hi, welcome to episode 7 of Data Every Day. Today we'll be taking a look at the classic Iris dataset. So let's go ahead and look at these columns. We notice here there's only 6 columns, one of which is our label column, and one of which is an index column. So we actually only have 4 features. It's a very small dataset, and it's been used in many machine learning introductions and tutorials. So let's get started. Just bring this over and start by importing our libraries. Today I'm going to use something called pandas profiling to get a better sense of our data. Don't need that. Alright, we'll get some pre-processing tools. We used a standard scaler today. And as always, our nifty train test split. Alright, and we'll be using TensorFlow today to train neural network on the data. Even though it's a very simple data set, I felt like using TensorFlow. So, get an input layer. We'll get dense layer. And we'll get the model. Alright, let's import everything. Alright, so first let's read in our data. And we get the file path from right over here. Get iris.csv. Take a look at it. And there we go. Alright, let's immediately drop this ID column because we want 0 indexed rows. So data.drop ID axis 1 in place true. Alright, so we have 4 feature columns and a label column, which if we could check how many unique values. I mean, I already know the answer. It's 3. There's 3 species we're trying to classify. But let's use pandas profiling to get a better sense of what we're looking at. So, profile report. Profile equals profile report. And then we can, let's see, profile dot to notebook iframe. And data goes in here. Alright. Alright, here it is. Okay, let's put this in its own window so we can get a better view. Alright, right here. This is our pandas profiling report. Very nifty utility that gives us all sorts of information about our features and just the data. So we can see for each feature it gives us a distribution, it gives us all the stats about each one. And it looks like yeah, these do follow a pretty normal distribution. And it looks like these two have more of like a bimodal look. So this suggests that out of all of the flowers, the sepal length tends to stay around a single mean. So that would mean that all three species sort of share a mean value for sepal length. Same thing goes for sepal width. But for petal length and petal width, we can see that it looks like maybe one species or two species have a very low value, and the other species or two species have a higher value. That's why we see two means. The same thing goes here. So it looks like we have 50 of each species, so we have uniform class distribution. And up at the top it says warnings. So apparently we have 3 duplicate rows. That should be alright. And it says that petal width is highly correlated with petal length, and that petal length is highly correlated with petal width. So let's take a look at that. We can see the correlations here, petal length and petal width, and we can see, yeah, there's quite a linear relationship between the two. This is not so much of a relationship between the sepal length and sepal width. And it looks like between the sepal length and the petal length, there's something of a linear relationship, but then also this it's almost like there's two relationships happening. This plays into what we saw earlier with the two means. There's something else happening with one species at the lower areas, and something else happening with the other species at the higher areas. And you can see less of a relationship, but still we see that guy down there. And no relationship between these guys. Not really much between here either. Alright, so here's a correlation matrix. And we can see there is a high correlation between sepal length and petal length, and sepal length and petal width. And as we saw earlier, petal length and petal width are highly correlated with each other. But we do see that sepal width is not correlated with sepal length, and that there's actually something of a negative correlation between sepal width and petal length, and petal width and sepal width. So we have some sense of the data set now. We can see there's not sure what it means by missing values. This is just a count of our this is the whole data set's only 150. So I'm not sure what this means by missing values. Alright, so let's get into it. We'll start by why don't we split off x and y? So y will be our species column, and x will be the data set without the species column. You see y should be a vector of our species, and x will be the whole data set without it. And because y is not in numerical form, we're going to use sklearn's label encoder to transform it into a numerical format. So encoder equals label encoder, and we will say y equals encoder dot fit transform y. So what this will do is the encoder will look at y, find all the unique values, and assign a numerical label to each unique value, and then redefine y in terms of the numerical values instead of its initial text labels. So now we can save those mappings. We'll call it y mappings, or we'll see species mappings is going to be a dictionary index to label for index and label in encoder.classes underscore. And if we just take a look at that, you can see, oh, what happened here? Too many values. Oh, here. Oh, yes. The reason is this guy is actually just a list. So we're going to have to enumerate it so we can turn it into a dictionary. Oh, here we go. Alright. Oh, let's redefine it. I did it too many times. There we go. Okay. So we can see 0 has been mapped to Iris Dataset, 1 has been mapped to Iris Versicolor, and 2 has been mapped to Iris Virginica. So now if we ever need to reference back to what these numbers mean, we have this species mapping variable that can tell us. So if we look back at Y now, it's just an array of 0s, 1s, and 2s, depending on this mapping. Alright, so let's see what to do next. Okay. So this dataset, the values don't really take on a very large range. They're all pretty compact within a certain small range. But I think let's just apply the standard scalar just for good practice. So scalar equals standard scalar, and x equals scalar dot fit transform x. Okay. Now we look at it again. We'll as a data frame, because the transform function turns it into a NumPy array, so we have to put it back in data frame to get this nice view. And we can see everything has been scaled with unit variance. So the each feature's variance is going to be it's been centered with a mean at 0, and the variance will be 1 for every feature. Okay. Actually, I want to see something. X dot describe. Okay, I was wrong. It doesn't center a mean at 0. All it does is yeah, you can see the standard deviation is 1 for every single feature. So all it does is change the mean. We did not perform mean normalization. Okay, so we scaled it. Now I think we're ready to train. So we'll use train test split, xtrain, xtest, ytrain, ytest, train test split, x, y. Because this is such a small data set, we'll have our train size to be a little bigger. We'll do 70% rather than 80. And so that will shuffle our columns as well. You can see that it was all ordered by species, but that will change now that we've done this. To get an example, we could do ytrain. You can see it's been shuffled around. Alright, so now we'll use TensorFlow to build a model. Inputs is going to be the Keras input layer with a shape, and because we have 4 features, right? Let me just bring that back to x. We have 4 different features. We're going to input a vector of length 4. And so our intermediate layer, our hidden layer, is going to be a dense layer with 16 nodes, since it's such a simple data set, and ReLU activation. And we'll feed in the inputs. And outputs is also going to be a dense layer, and we only have 3 species, so it will be with 3 nodes, since this is our output layer, and a softmax activation. Feed in the x, and then our model will be our tf.keras.model, with inputs defined as inputs and outputs defined as outputs. Alright. Shape is not, oh, I didn't put an equals. Alright. So let's get a better look at the model, what it's doing, model.summary. And we can also do tf.keras.plotModel to get it in a graph form. Alright, so what happened? Oh, tf.keras.utils.plotModel. Alright, so here we can see 3 layers, an input, a dense layer for our hidden layer, and a dense layer for our output layer, with a total parameters 131. And we can see just a graphical format, very simple model. That's what it looks like. Alright, so let's compile it. And we'll use our optimizer as an atom optimizer, and our loss as sparse categorical cross entropy. In metrics, accuracy will work since we don't have skewed classes, and we'll compile it. We'll define a batch size of 32, and we'll run it for 1,000 epochs to start. And I know that sounds like a lot, but it's better to do too many on the first go so that we can plot a learning curve and figure out how much we need to reduce it by. So we will store our model's fit in the history variable. History is model.fit, xtrain, ytrain, the batch size of batch size, and epochs given by epochs. And we'll also include a validation split. So 20% of the training set will be our validation data. Alright, let's do it. Batch size. Oh, I didn't run this. Okay. Alright, and that's going to go for 1,000 epochs. This is such a small data set, though, that really shouldn't take very long. Let's take a look. And we can see very high accuracies since there's such a clear relationship between the features, and it's such a simple. It's like we're using a super powerful model on such a simple data set. So we're getting very high accuracies, and you can see there's not really too much overfitting going on. Alright, we finished our 1,000 epochs, and now we're going to get a plot of the learning curves for the data for the training. So plot.figure, fig size is going to be, we'll say 14 by 10. Plot.plot, and on the x we'll have a range of all the epochs that we trained for, and on the y we're going to have our training loss. So again, history is our fit. History.history is hold on. print I. Okay, so history.history has basically all our metrics stored as arrays or lists. And so this guy, this guy, this guy, this guy is all stored in history.history. So we can access the loss, which is just our training loss, right? Over, and it will be graphed with respect to the number of epochs. So let's see, okay. Let's make this guy blue. And we'll do the same thing, but for the validation loss. So history.history. Instead, we'll use val loss right here. And we'll make this red. Alright, and we'll just add some more information. Title. Learning curve. Curves for training validation loss, and we'll put an X label. It's the epoch, and our Y label is our loss, and we'll include a legend for the red and the blue and the red. We'll have training loss and validation loss, and then plot.show. Okay. Alright, so we can see over the course of the 1,000 epochs that we trained, our training loss, which is the blue line, oh, what happened to our legend? It's not showing up. Hold on, let me just see what's going on. Aha, I see. Okay. Oh my god. Plot.show. And I put a comma here. This should be one. That should be one guy. Alright. So now we have it. Alright. So we see the blue line is constantly decreasing, as it should. But the red line is actually going up. What does that tell us? The model is overfitting our data. Because it's getting really, really good at learning the training set, but it's doing an increasingly worse job at generalizing to new unseen examples. So what we need to do is find at which point along this curve do we have both a low training loss and a low validation loss. And you can see the validation loss doesn't really start increasing until after 400. It starts going back up again. So at 400 it looks like we have a pretty good validation loss, which means at this point in the training cycle, it is doing a very good job at generalizing to new unseen examples. So we'll go back up and we'll change the epochs to 400. We'll redefine our model, recompile, and then train it again. This time only for 400 epochs. You can see it's already halfway done. And it's completed. So we'll plot it again. You can see now both curves go down and converge to a single point. So this is a very, very little difference between them. So this is a well-fit model now. So now we can go ahead and just evaluate it on our test set. Test y test and get 100% accuracy on our test set. So I mean that's remarkable. Again, it's a very small data set, so this isn't so surprising. Our model did an amazing job at learning the patterns in data, and we actually got 100% accuracy. But if we look at this length of y test, it's only 45 examples, so 100% accuracy on 45 examples is really not that impressive. However, very good job. So I think that concludes today's video. If you enjoyed it, leave a thumbs up and hit subscribe, and I'll see you guys tomorrow. Enjoy.